The last speaker today is Johannes Schmitt. He's going to speak in logarithmic double-ramification cycles.
Thank you very much for the invitation. Yes, so I want to talk about logarithmic double-ramification cycles. These are some cycles on the moduli space of curves cut out by some natural equality of line bundles. And quickly in the talk we're going to see that these cycles don't really want to live on the moduli space of stable curve itself, but on these blow-ups that Drew already mentioned. So somehow they feel more comfortable being in some blow-up. And if you give them this comfort, then actually they start behaving more nicely than if you force them to live on MG and bar. But so to do this, this laterally leads to the definition of the logarithmic Chow ring, which studies the intersection theory of all suitable blow-ups simultaneously. And then the main result that I'm going to talk about, which is joint work with Holmes, Molcho, Pandharipande and Pixton, is that we calculate an explicit formula in terms of tautological classes for this log double ramification cycle. And much of the talk will be about developing just the language to express this formula. Okay, but we start very simple on the moduli space of smooth Johannes G curves with n marked points. And so if you have the additional data of a vector A of n integers which sum to 0, then you can look at a particular condition on the curve. So a general curve will just be a smooth curve with n distinct markings. And then you can require that the curve should admit a finite ramified cover of the projective line, such that the markings exactly form the pre-images of 0 and infinity. And in fact, you want that this vector A gives the orders at these points. So somehow at I with AI positive, you want that the PI, the map has an order AI there. On the other side, with negative orders, you wanted to have a pole there. You can express this by saying that the divisor of this meromorphic function is the sum of AI PI. That's a very natural condition, and it cuts out a closed subset of MGN. And this is called the double ramification locus for the reason that somehow it parameterizes rational, somehow ramified maps over P1 with two, therefore double ramified profiles given. And so a crucial reformulation here will be that you can actually, the existence of this is equivalent to the equality of two line bundles on C. Namely, you can form the line bundle associated to the sum of AI PI, and I claim this condition is equivalent to saying that this is OC. The reason is just that somehow this here is a meromorphic section, so a meromorphic section here which has this divisor. So this proves that this is equivalent to this equality of line bundles. And so we want to do maybe intersection theory, and so just working on MGN is maybe too poor. We want to close it up. We want to extend it to some compactification. And not only this, closed subset, but also somehow its fundamental class, basically. And so we want to extend it to the moduli space of stable curves. I guess at this point in the conference it's a bit too late to introduce it, but nevertheless, somehow the moduli space now, we added some extra stuff, a normal crossings divisor, parametrizing nodal curves where the markings are still smooth and the set of automorphisms is finite. This turns out to be a nice, smooth, compact space, and the original thing lives in there, and then we can ask how do we extend it. And well, we have this very nice condition here, and we might, okay, so our first attempt is we could just write down exactly the same equality, because somehow, because the mark points are still smooth, this O sum AI PI still makes sense, and we could just look at this set. And the bad thing is this is not even closed. And now we should pause and meditate on this, because normally as algebraic geometers, we say, oh, this thing is cut out by an algebraic condition, so it's closed. It's an algebraic set. And somehow this fails now. So should we doubt our sacred traditions? Well, the thing that makes this rule work is that the equality should happen in some separated space. Then the equality of two morphisms cut out something closed. But this here is an equality in the Picard stack, the universal Picard stack parametrizing a stable curve together with a line bundle of total degree 0. And this turns out to not be separated, having to do with the fact that limits of such line bundles are not unique. And so this didn't give something closed. Okay, so we could say, well, we have learned our lesson, so maybe we should formulate the equality in something which is separated. And you can make this by taking an open substack here, which parameterizes still this line bundle, and now it should have degree 0 on every component. And this somehow, robs you of this non-uniqueness of limits. This is a separated open substack. But then we see we have kind of moved the problem around, essentially. I mean, somehow there was a reason why it didn't work the first time. Because, well, we have now this diagram. We have the Picard stack mapping to MGN bar, and then we have the two sections that we want to intersect, the trivial line bundle. This is good. This is a multi-degree 0 line bundle. This lands here. But then the other one, you see, this looks a bit sickly. It only gives us a rational map, I claim. And the reason is, well, if the curve splits in some components, then there's no reason why this O sum of AIP should be a multi-degree 0 line bundle. Because, I mean, the total sum of the AI was 0, but the subsets will not sum to 0 in general. Okay, so this didn't work, but, well, at least we have now this picture. And then a brilliant idea by David Holmes was, well, we have a rational map, so maybe we can just try to resolve its indeterminacy. Maybe we can blow up the domain of the map to make it as widely defined as possible. And then we try to intersect. And this leads to a very scary diagram, but we're going to go very slowly. Okay, so this is just the old diagram. And then he says, well, we can take a blow-up of MGN bar here. And in fact, it will be a particularly restricted blow-up. Namely, you just take some of the boundary strata of MGN bar, you blow them up, and then you take the strict transforms, and you have more projective bundles, and you can basically just blow up strata in these normal crossing pairs that you get. Do this a couple of times. And then after that, now it would be nice if I could say, okay, after blowing up, the indeterminacy is resolved. But this doesn't quite work. It's still, you need to still throw out some stuff. So you have an open subset here on which somehow these two sections extend. So somehow this is basically birational, so somehow this is basically determined. Now you might say, okay, well, take this MGN bar, take this set where it's defined. What have we gained? So what Holmes shows is that there's a kind of universal largest birational thing mapping to MGN bar on which these sections can extend. This M diamond, and this is defined by such a universal condition, and it sits inside some log blowup, and so somehow this is then the biggest one that you could hope for. And the reward for this work is that then when you actually intersect these two sections set theoretically, so you look at this dr locus here, then you get a compact space. You get something which is actually proper. So it looks like nothing more is missing. So you should have captured everything. And so this is then good enough, because then, for example, if you want to define a closed subset of MGN bar, well, just take this proper space and take its image under this composition here. Since the domain is proper, this is a proper morphism, this composition, and so its image is a closed subset, this is a double ramification locus. And then...
Is it possible to tell us the simplest example which is in this space which wasn't in your naive space?
Yes.
Ah, very good.
I mean, okay, maybe it comes later then, but I come back to the question. Okay, and okay, and then, well, we also want to do intersection theory. So what we can do is we can not just take the set theoretic intersection, but actually the cycle theoretic intersection. So for example, you take the image of one and then you pull it back. And then this is a cycle. I no longer have a... Okay. This is a cycle which is supported on this double ramification locus on the set theoretic intersection. And this is good to know because then you can push it forward to MGN bar under this proper composition. Okay? So you couldn't, if you just had the cycle here, you couldn't really push it forward because this thing is an open embedding. Okay. And then this is the classical double ramification cycle. And it so it lives in M bar, and in fact we can kind of end wave our way to a dimension estimate, namely, well, the Picard group of a genus G curve is G-dimensional, and you intersect two sections of this G-dimensional vibration, so you expect this to be codimension G, and indeed this lands in codimension G. So in the talk, I will work with this Chow ring, this kind of algebraic version of intersection theory. If you're more comfortable, just take Poincare duals and then think about the cohomology. It's also fine.
Do these M diamonds have modular interpretations?
Yeah, so basically they have a modular interpretation as saying that you have a curve and then you also have something which we will see later. You have a piecewise linear function on this curve, so some log, means the log modular interpretation, which balances out basically the multi-degree that wasn't zero here. Something like this. But we are going to actually see this a bit later as it's going to come. Okay. And so we got our hands on some cycle classes, and I just wanted to give a small overview. So there's actually a lot of things that you can do with them. So first of all, this condition OC is the sum of AI pi. This can be generalized. You have another natural line bundles on C, namely the canonical line bundles or the dualizing sheaves. And you can then the sum of AI must be the degree of this omega C to the K. And you can generalize this whole story for this. This basically says there should exist a K differential with zeros and poles at the marked points. And then this was used by various people, by Sauvager, to study moduli space of flat surfaces. And a joint paper with Costantini, Sauvager, we took intersection numbers of these psi classes. And Costantini, Möller, Zachhuber used this to compute orbifold Euler characteristics of strata of differentials in the Hodge-bundle. So there's some application in this direction. Then also, of course, as in Drew's talk, we are interested in seeing, do these cycles live in the tautological ring? And so this was proven. There was actually a formula given, a very nice formula in work by Yanda, Pandharipande, Pixton, Swonkin in the setting that I presented. So for k equal to 0, just the OC here. And then to generalize it to omega c to the k, there was some joint work where we then also managed to prove a formula. Okay, and then other people can also use them. So you can define integrable systems, the so-called double-ramification hierarchy, having nice properties, the solutions, and also in chromophyton theory. So, for example, Oberdig and Pixton used it to study chromophyton cycles for elliptic curves and showed some nice properties there. Okay, so this is just to say, okay, this thing is already interesting. But the whole twist of the talk is that we get something slightly better. So if we look back to this diagram here, where we had this cycle, the set theoretic intersection, the cycle theoretic intersection living here, we pushed it forward all the way to MGN bar, but we could make a pit stop in the middle and just push it forward to this log blow-up here. And then, whatever this cycle class is, it must contain at least as much information as the dr, because you can recover the dr from just pushing forward further. So it's some kind of refinement. So before we talk about the virtues of doing this, we should face some issues, namely the first one, which I have swept under the rug a bit, is that this ambient space, this bar space, is actually not so canonical. So somehow this open subset, this here is canonical, and it sits inside different compactifications, but it's not totally clear which one to take. And basically, this is really on the nose the same combinatorial problem, like if you have a quasi-projective toric variety with a given incomplete fan, there could be many ways to fill in this to complete fan. And this is the same flavor of problem. The other thing is that this space here depends on A. So each of these cycles wants to live in its own space, but sometimes we want to make them talk to each other. And so, okay, how do we solve this problem? And this is exactly the notion of the logarithmic Chow ring. So we just...
Sorry, can you remind me of the capital A's? Is that just the data of the little a's? Or what was
this is the data of the multiplicities at 0 and infinity. This is this kind of vector summing to 0. Yeah. And then the logarithmic Chow ring of MGN bar is just defined as a direct limit of Chow rings of all log blowups of MGN bar. And you can actually make this precise. You can say this thing here, you take the set of all log blowups and the cycle class on that blowup, and then you have an equivalence relation saying if you have one log blowup and then you blow it up a bit further, then the cycle m hat and the class alpha living here should be identified with its pullback to the further blowup. So you can always blow up more and just take the total transform of the cycle. And the slogan is these things should describe the intersection theory of all log blowups simultaneously. And the good thing is that if you take any such choice as above for compactifying this diamond space and take the double ramification cycle there, then this is a well-defined element in log Chow of MGN bar. It's independent. And so now all of these things sit inside here and they give some canonical elements. Okay, this is the logarithmic double ramification cycle and the title of my talk. Okay, and so why should we go to this these lengths to do this? So here's some properties of the log double ramification cycle which are false for the classical double ramification cycle. So the first one is basically what got the story started in joint work with Holmes and Aaron. We proved that if you have two such cycles for vectors a and b and you multiply them, this is the same thing as taking the log dr of a times log dr of a plus b. So why is this? Well, this parameterizes basically the condition O sum ai pi is trivial. And this, the condition O sum bi pi is trivial. And then, as you learned in grade school, if you have two equalities of line bundles on a smooth curve, then you can tensor them to get an equivalent system of line bundles. And so if you just tensor the second condition with the first one, then you get this here. And so somehow, at least intuitively, you would expect that this holds, and this can actually be made precise, but you need to work on these blowups. And in fact, for the classical DR cycles, there's just false. You can just write down an example in M bar 1, 3, which just fails. Okay. And then maybe also enumeratively, there's these so-called double Howitz numbers. They count covers of P1 ramified with fixed ramification profile over 0 infinity and simple ramification at other fixed points. Very nice enumerative invariance. And Cavalieri, Markvik, and Druff showed that you can actually recover these by intersection numbers of log dr with some other class. And this is really like an enumerative geometer stream, this formula, because the log dr parameterizes the condition the curve has ramification over 0 infinity. The other cycle parameterizes the condition the branch points are fixed. And I mean, somehow this is really the poster child of intersection theory. And then you can also kind of go in this direction of taking this k deformation, so the omega c to the k, and then you can use log dr, and this was done in their paper and recently also extend a bit further. You can use this to define enumerative invariance by taking intersection numbers in the log Chow, and for tropical reasons, these are called k-leaky double Howitz descendants. You can ask Druff why he chose this. Okay, why they chose this. Okay. And so, so these cycles have some very nice properties, and what I want to discuss in the rest of the talk is this paper with Holmes, Molcho, Pandharipande, and Pixton, where we compute this thing explicitly. So before, there were already some work by Holmes and Schwarz, and by Molcho and Druff, who either showed some very theoretical statement that this lives in a certain part of log Chow describable by the stuff that we are going to see later, and then Druff and Sam Molcho showed that you can in fact get them by starting with the DR cycle by the push forward, and then you can kind of climb up and take strict transforms and kind of recover what they were before pushing down. But this was maybe less explicit, and now we have a very nice explicit form. And the goal for the rest of the talk is basically to develop the language to state the shape of our result and explain some of the ideas going into the proof at the end. Any questions so far before? So the first thing that we need to describe for describing a log Chow class is we need to describe on what log blowup it sits. So we should think a bit about how to describe these efficiently. And so here is just a cartoon picture of M bar 1, 2. So you see it has many different strata. Generically, the curve is smooth, and then there's two kind of divisors corresponding to ways in which you can develop nodal singularities. And then there's two zero-dimensional strata where kind of the two singularities happen at the same time. And these locally closed subsets, the strata of this space, they are described by the stable graphs. And these graphs, for example, these here form a pair, so somehow they have one vertex for each component of your curve. It's decorated by the genus of that component. and then they have one edge for each node of the curve. A node connects two components, so the edge corresponding to it connects to two vertices. And then finally, you want to remember where the legs went, so there's little, where the markings went, so there's little legs in the graph to describe this. And you can just enumerate these combinatorially. And now we come to an actual example of one of these DR cycles where we see what kind of log blow-up is necessary. Okay. Oops. So let's look at the double ramification cycle genus 1 and partition 3 minus 3. Then the defining condition on smooth curves is that this equality here is satisfied, and this is equivalent, in fact, to saying that P2 is a 3 torsion point in the elliptic curve C, P1. Okay, so if we see M bar 1, 2, somehow you can see it as the universal curve over M bar 1, 1, so basically these vertical slices here are the fibers of this vibration. And then, so if you fix the C, P1, then you expect 9 3 torsion points. So this is kind of a 9-sheeted cover here. And then you can ask what happens with this condition when we go to the singular curve. So when the curve becomes singular, kind of 3 of the 3 torsion points plod along just fine, and all the others kind of crash into this into the node of the singular fiber. And you can see, I mean, somehow maybe this doesn't look. This looks like danger zone. And in fact, it would be the case that these SA, these sections of the Picard of margin equals 0 would not be defined here, and you couldn't extend it anyway. So somehow this is where you would get something non-closed. And then the log blow-up that you can take is somehow resolve this by introducing basically a chain of two P1s, and then at least the car crash is a bit alleviated, so diverted to 2 intersections with multiplicity T3. And in fact, then this S hat is defined everywhere except for maybe these 3 nodal points. But in particular, where the action happens, everything is defined. And so if you intersect them, you get the closed subset here. Take the image, and you get the double ramification locus. Take the push forward, get the double ramification cycle. Okay. And so we saw we already had to do a slightly tricky operation here, kind of doing a weighted blow-up at this point. So how do we describe these log blow-ups efficiently? And the answer, as Truth said, people who say log a lot also say tropical a lot. No, the answer comes from tropical geometry. And so here we go even further and first look at toric geometry, because if you have a toric variety, then it has a nice describing fan, a collection of cones in some vector space, and there is a dimension and inclusion reversing correspondence between the strata of the toric variety and the cones here. For example, this green cone would correspond to this point, and then the 2 rays here would correspond to the 2 divisors intersecting in this point. So it tells you a perfect description of the combinatorics of this. And then the log blow-ups of such a thing are then just described in terms of subdividing the fan. So cutting some of the pieces of the fan into smaller pieces. So for example, if you want to blow up this point, then you take this green cone associated to it and cut it through in the middle. And then you get the toric variety of the blow. Then you get the fan of the blow-up toric variety. So log blowers correspond to subdivisions. And so for the moduli space of stable curves, I mean, this is rarely a toric variety, but there is still such a collection of cones associated to it. And this is the moduli space of tropical curves. So here, just as a quick crash course, so a tropical curve is just the data of a stable graph together with some edge length, which are positive real numbers. And then if you fix G and N, you can try to write down a moduli space of tropical curves, just parametrizing all this combinatorial data. And this turns out to be a nice moduli space over kind of cones, and it becomes a cone stack. So, so here is the geometric picture, and here is the kind of cone stack picture. So let's go very slowly. So for example, for a smooth curve, you have a trivial graph. There's no extra data here to add. There's no edge length, so you just get a single tropical curve with this underlying graph, a single point. And then for the 2 stable graphs with 1 edge, well, you have 1 free parameter. You can associate a positive real number to it. So this gives you 2 rays, like this. And then there's the situation in which both of these singularities appear at the same time. And here you see somehow you can just independently associate it 1 length here, 1 length here. So you get a whole quadrant like this. So this would be the cone parameterizing all possible length assignments here. And it fits nicely in this because, for example, if you let the length of this edge go to 0, then these two vertices fuse and you just land at this point here. So you basically glue these things together. And here, somehow there is some twist here. So for this stable graph, you can assign two lengths, but they are not ordered. You don't really know which is x and which is y. And so you don't get a full r greater or equal 0 to the 2, but you get kind of this modulo, the thing which flips x and y. So you get a kind of stacky cone, just a half cone, not like this. And if you want to, for example, construct the underlying topological space of this cone stack, you just take the union over all stable graphs of kind of the length assignments on a nailed down graph where you have enumerated all the edges. And then you just glue them together according to either these kind of edge contractions, which we have seen, or to automorphisms of the graph, like here. So the precise details are not super important, but you should just remember there is, again, a kind of collection of cones sitting nicely together. And the cones correspond to the strata on the other side. And so they describe the combinatorics of the boundary stratification. Okay. And then the nice thing is that this the toric situation generalizes. Some of the log blowups of M bar just correspond to subdivisions of this cone stack. So for example here in gray we have the picture from above basically. And then when we want to take this blowup for the dr3-3, this introduced these two exceptional divisors. This corresponds to basically subdividing the stacky cone at this point, and then if you unfold it, you would see the second thing here. So these two inserted rays correspond to the two exceptional divisors here. Okay. So that's already a very nice data type for writing down a formula. You just have this kind of cone stack and you chop it into pieces. The second thing is that now that we have such a log blowup, how do we describe interesting cycle classes on there? And this is where the next piece comes in, namely the piecewise polynomials on this cone stack. So if you have such a subdivision of the moduli of tropical curves, then a strict piecewise polynomial is just a continuous function from the underlying topological space to R, which you require to be on each cone of this cone stack to be a polynomial in the edge length on each of these cones. So for example here, on this cone stack, if you don't subdivide it, you just take the trivial subdivision, then you can write down a function f continuous to the real numbers, which is kind of 4x squared plus 8xy plus 4y squared on the upper side, and it's 4x squared plus xy on the lower side. And so this is, of course, given by polynomials on these cones, and it's also continuous because you can check on the overlap. When you set y equals to 0, this kills these two terms and this term, and so both are given by 4x squared, so this fits together nicely. Okay, so this is a piecewise polynomial on this fan, or a strict piecewise polynomial, and the piecewise polynomial is just a continuous function, which you can make into a strict piecewise polynomial by chopping the fan up into some pieces. So for example, on here, on this upper cone, you could take something like minimum of x comma y. This would be a function which would break along this kind of flipped edge. So it wouldn't be really on the upper part of the stacky cone. It wouldn't be given by one polynomial, or the same one as here. And but if you then subdivide it at this thing, then it would be given by such a thing. Maybe, yeah. You can also think of less confusing examples if you subdivide this. Okay. So piecewise polynomial just means you can find some subdivision which makes it a polynomial on each cone. And so these things form Q algebra, so you get these rings. And now these rings are exactly the right tool to describe nice classes on these blowups. Namely, this was proven in this paper by Holmes and Schwartz, that there exists a unique ring homomorphism, or Q algebra homomorphism, from these strict piecewise polynomials on this subdivided fan, a subdivided cone stack, to the Chow ring of the corresponding blowup. And it is characterized by two conditions. The first is that on piecewise linear functions, we know exactly what happens. Namely, if f is piecewise linear, so it's given by a linear polynomial on each cone, then we want to send this is also graded morphism, so we send it to a Chow 1 class, so basically divisor. And what you do is, the rays in this cone stack correspond by this kind of strata cone correspondence. They correspond to divisors, so codimension 1 things in M hat. So if tau is a ray, then you have a divisor d tau, and you want to take its fundamental class and sum it up with some multiple, and the multiple is exactly the value of this piecewise linear function at the primitive generator of the ray. Okay, these were a lot of words, so let's look at an example. So here we have a perfectly nice piecewise linear function, which is x plus y here and x here. And then this formula tells you go through the two rays of your fan, and then look at what does this function do at the primitive generator. And so here, at this primitive generator 1, 0, if you evaluate it, you get 1. And at 0, minus 1, if you evaluate it, you get 0. And so this recipe tells you this should be sent to 1 times the divisor associated to this ray. This was the irreducible boundary divisor, plus 0 times the other one. So this thing just gets sent to delta ir. And then if you want to have the other boundary divisor, you can also arrange this. You can take the function 0 here and minus y here. This has values 0 and 1 here. And so it gets sent to 0 times delta ir plus 1 times the boundary divisor with separating edge. So this is basically just a fancy way to encode a linear combination of these boundary divisors in M hat. Okay? So this happens on piecewise linear functions, and then already in this example, this would tell us where this f goes, just as a remark. So this f here, well, it was cleverly chosen in such a way that it's actually 4 times f ir squared minus f ir times f0. And so this is a ring homomorphism. It must get sent to 4 times delta ir squared minus delta ir times delta 0. So these two rules already tell you something about higher degree polynomials. So this might not always work. You might not always be able to decompose a strict piecewise polynomial as a polynomial in strict piecewise linear functions. But this is true if you manage to subdivide your space a bit further. And then the second rule says that this phi should be compatible under further subdivision. So somehow you can take this sigma hat and chop it into more pieces, then you get sigma double hat. And any function which was already a polynomial on each of the pieces here is still a polynomial on each of the pieces after. Then you can take the two phi functions, these land in the Chow rings, and then this being a subdivision means that there was some log blow up here, and then you can complete this diagram by saying the Chow ring of M hat maps by pullback to the Chow ring of M double hat. So it should be compatible under this exactly this equivalence relation that you are allowed to replace a class by the pullback to a further log blow. Okay. And so these rules together determine, first of all, these ring homomorphisms, and then in fact, this is why we introduced this PP star. So you can also, whenever you have any piecewise polynomial on this, then just, well, take the subdivision on which it is a strict piecewise polynomial, apply this, then you get a Chow class on M hat, on this log blow up, and then this is a representative of a class in this log Chow. And the fact that this diagram commutes tells you this was independent of which exact thing you chose. Okay, this was all a bit dry and abstract. What I just wanted to mention is that we also show like what kind of classes do you actually get by this recipe. And the answer is on this M hat, what you can describe in this way is exactly take some stratum of this log blow up. This has some normal bundle, might decompose into direct summons, and what you can get is you can get the fundamental class of the stratum decorated by churn classes of some of the normal directions. And at least somehow in this picture here, I mean, this 4 times delta ir squared minus delta ir times delta 0, if you have done the second theory on M bar, you see this will exactly be of this form, will be strata, and maybe if you have some excess intersection, then you will have the normal bundle classes. So this is the stuff that you can get by this recipe. Okay. Any questions so far? Okay. Then let's get to the shape of the formula. And mercifully, I will not tell you the full formula. I will just tell you the shape of the formula. Okay, so this is the theorem. So we have input data as before, and the formula will combine kind of classical tautological classes. Namely, we can define this eta to be just the sum of ai squared, ai are the components of this vector, ai squared half times psi I, the cotangent line class. A priori, this is a class in Chow 1 of M bar, but M bar is its own trivial log blow-up. So this also defines a representative of a class in log Chow. And in fact, you can see that the Chow ring always sits inside the log Chow. So this was the kind of algebraic contribution, and then come these kind of piecewise linear things in. Namely, we say there is an explicit subdivision sigma hat of sigma mgn bar. This will define us a log blow-up. And there exist these piecewise polynomial functions fl of degree 1 and fp of mixed degree, such that the log dr is given by a relatively simple formula. Namely, take this eta plus phi of this fl. So these will both be kind of log Chow class. So this is a log Chow 1 class, a logarithmic divisor class. And you can plug it into the exponential power series. Then you get a mixed degree class. And for good measure, you multiply by this phi of fp, by this piecewise polynomial mixed degree class. So now you would have a sum which is supported in basically all degrees, which are possible. And since this lives in codimension G, well, you better take the codimension G part. And if you do this exactly, you get the log double ramification cycle. So maybe for the people who have thought a bit about DR cycles, so basically over the moduli space of compact type curves, this thing would actually vanish. All the contributions there live over the complement. And so this here is basically just some kind of this eta plus phi of fl. You should think of this as being basically the pullback of this theta divisor. And then there's the kind of Haynes formula on compact type, just says take some concrete divisor class, raise it to a power g, and divide by g factorial. And this is exactly what this exponential would tell you.
So if you don't take the codimension g part by other degrees, do you get relations? Or?
Yes, so somehow it follows from work of Yang and Bei that then you get relations if you take the codimension g plus 1, g plus 2, and so on part. The lower codimension parts are still kind of a bit of a mystery what they do, but yeah, you can get log tautological relations like this.
So you know that for lower g that they are not relations?
No, in general, I mean, even for g equals to g, they are not relations, and then the lower terms, I mean, yeah, it's not so clear what they are.
So A only enters through theta, or?
Well, the A enters through, I mean, somehow everything is swept up in this, both the sigma hat and what these piecewise polynomials are. So this everything depends on A, yeah. Maybe I should have said this, but somehow, yeah, I mean, this is a very straightforward way in which the A's enter, but this subdivision is really very much dependent on which you have. And I think that this is kind of philosophically nice because it mixes these classical tautological classes with these piecewise linear classes, and together they can work to define this cycle. Okay, and so I wasn't very explicit about what this explicit subdivision is, but we are going to see when I now talk about the idea of the proof. We're going to see a bit where this comes from. Okay, so this subdivision is actually related to moduli spaces of stable line bundles. I thought I can try to fit in a bit with the spirit of the conference and say something about stability conditions and so on. These are moduli spaces of both curves and yeah.
The n diamond does not work as a solution.
Sorry, which one?
The diamond work.
So somehow the n diamond would indeed give you kind of not really a subdivision of the whole sigma mgn bar, but somehow of some subcomplex. Because the m diamond not being projective or proper is reflected in the fact that this would only give you kind of an incomplete fan sitting inside mgn trop.
Where it sits. I meant the person.
Yeah. So somehow this sigma hat, yeah, we are going to see this. The sigma hat, the corresponding thing is actually exactly giving you the birational model of mgn bar on which the dr hat sits, on which the log dr cycle is supported. Yeah. Okay. So we want to talk just a bit about stability conditions of line bundles on curves. And here it will be nice to allow the curve to become a bit more special, namely a quasi-stable curve is what you obtain from a stable curve by choosing some of the nodes and replacing them by just a single P1. So some are not chains of P1s, just a single P1. So you have these unstable rational bridges of length 1. And then a universal stability condition is kind of numerical data for any such choice of a quasi-stable curve. So it's an assignment of real numbers for any quasi-stable curve and any component on that curve. Each of those gets a number, like this. And they should be compatible both with kind of deformation, so it should only depend on the shape, the topological shape of this thing, and they should be compatible with smoothings, which means that if you smooth one node here, then basically you get a new component and then the numbers are just added together.
So does that mean that you have to assign 0 to an unstable rational bridge?
Yes, this is exactly somehow this follows them. Yeah. And so this was studied by Kaspargani and Melo, Molcho, Ulrich, and Viviani, with the goal of setting up moduli spaces parametrizing exactly a curve and a stable line bundle. These are these so-called compactified Jacobians. And we call a line bundle L on C admissible and semi-stable for this data. So admissible part is basically that its degree on these unstable components should be 1. And the stable or semi-stable part means that if you have any subcurve here, then the total degree of the line bundle on that subcurve is not too far away from the sum of these numbers on the corresponding components. And you can make this precise with this exact shape here and some more quibbles. But for example, for this picture, I mean, very much the stability condition suggests that maybe you should have degree -2 here, 1 here, and 1 here. This would certainly be fine. And if you, sometimes you have a bit more wiggle room to have a slightly different multi-degree. Okay. And so these were all the definitions for individual stability conditions. And we don't want to work with all stability conditions, but we want to have two properties. The first one is that it is small. This just means that all the numbers are relatively small. More precisely, you can characterize this by saying that for any line bundle on a stable curve, which has multi-degree 0, it is actually stable. And this has to do with the fact that in the end we want to basically land in this PIC multi-degree 0, by whatever construction follows. And non-degenerate just means stable equals semi-stable. And you can always reach this by just having these numbers be a bit, wiggle them a bit, and then none of these inequalities can become a strictly equal. So these are easy to find, but there is a kind of choice. There will be different stability conditions having this property. And for such a stability condition, we can write down a new moduli space. And this is a moduli space parametrizing a quasi-stable curve with marked points. And then the additional data that we have here is similar to Francesca's talk. We have a piecewise linear function on C hat. So if I were honest, then I would have to say something about monoids, and somehow you have basically the ghost sheaf or of this C hat, and you have a section of this. You can see it like this. For me, I will just basically talk about the combinatorial shadow of this, because piecewise linear function, you can also see it as basically just being a function from this kind of tropical curve to the real line. And for such a function, you can record what are the slopes and directions of some of the edges. So in this case here, it would say, on this edge, the function has slope 7, and on this edge has slope 3, and this edge is actually contracted to a point. So what does this combinatorial data give you? It gives you exactly such a twist of the trivial line bundle. So in Francesca's talk, we also saw if you have such an alpha, you can associate to it a line bundle. And in this case, I'm not going to really say what the line bundle on the full curve is, but I'm going to tell you that on each individual component, you exactly recover line bundle, which is just associated to a sum of the pre-images of nodes. So in this case, because, for example, on this component, it receives two edges with slopes 7 and 3. And so on this component, you would have the line bundle O7 times P plus 3 times Q. And there's always a price to pay. So on the other side, you have then O minus 7 times P and O minus 3 times Q. Okay, so this is this kind of twisting line bundle determined by this alpha. And then the actual condition here is that you start with the line bundle that you might be interested in the end, this O sum AIPI that we want to be trivial. And this might not have multi-degree 0, but then this alpha can help you shift to a multi-degree which is hopefully relatively close to 0. So if you twist with this OC hat of alpha, then you get a new line bundle. We call this L alpha, and the condition is just that this is admissible and stable. So you can kind of get into this regime of admissible stable curves. Okay, so these were a lot of definitions, and now there's some payoff, because actually the first thing is that this moduli space is a log blow-up of MGN bar. So if you have the forgetful map, which kind of forgets the alpha, stabilizes the curve, this lands in MGN bar, and this thing is a log blow-up. And inside there we have a nice open subset, which is just a subset where the C hat is actually stable. It didn't develop any of these unstable bubbles, and the L of alpha is then multi-degree 0. And so having a log blow-up and having an open subset, this might remind you of something at the beginning of the talk, and indeed the nice theorem is that you can exactly, for this diagram which we use to define the log dr, you can exactly take this moduli space here, so this is the theta stable bundles, you can take this as the log blow-up and this here as the open subset. And moreover, then the section as set of alpha, this extension of the section that we started with, is exactly the section sending each bundle here to L alpha. So everything becomes suddenly explicit. So somehow in this non-canonical world where we could choose some log blow-up and so on, we have now found a nice explicit representative. In particular, the sigma hat from the theorem, the subdivision, is exactly the subdivision corresponding to this log blow-up. Okay. And so, and now we have everything ready. So this is the space on which we want to make our stand and do the calculation. And this space has one nicer property. Because if you remember, the process to get the log dr was now slightly weird. Because we wanted to intersect these two sections, and we get a cycle on the set theoretic support, and then push it forward to here. And somehow in intersection theory terms, that's a weird thing. I mean, somehow having something supported on some compact thing and then pushing forward, this is not nicely expressible in terms of formulas. So we would very much like to work on this space here, just do some intersection of things there. And this can actually be made to work. This is the next scary diagram. Okay, so we have the full MG hat theta here, so the full space. It has nice part, which is away from the red stuff, and then it has this red stuff, which is kind of the complement of this open set. And we want to avoid this red stuff creating trouble. Now, here we went to this pick of multi-degree 0 line bundles, because this L of alpha has this property. If we want to extend this to some section which makes sense everywhere, then we have to relax our target. Namely, this lands now in a very scary Artin stack, namely the universal Picard stack parameterizing any nodal curve of genus G and any line bundle. You can really forget everything here, all the conditions. Certainly this here is nodal and this is line bundle. Okay, so it lands there. And then, if you remember, I mean, here we would want to intersect with this S0, with the section which sets L to 0. And now this Picard stack has, of course, the subset where L is the trivial line bundle. And we call this E. But since it's not separated, again, this is not a closed subset. And we can take really the dumbest thing possible. We can just take the closure. Okay, then we have something closed. That's fine. And in fact, we saw this a bit in Drew's talk, because this is the set of all line bundles which can be approximated by a family of smooth curves and a trivial line bundle. So here this thing actually features again. So we have this closed subset, and now we just take the pullback of this, first of all, of this set, and then also of the fundamental class of this thing. Now we observe on the good locus, this L alpha and the intersection of S0 exactly gave us what we wanted. It gives us this double ramification locus, and set theoretically it gives us the double ramification cycle. But we could still be spoiled by this red part. And the great thing is that all this nonsense with the stability conditions guarantees that the red part moves far away from the green part that we pull back. This is the final miracle, somehow. So the claim here is that this maps this red complement away from E bar. I'm not going to maybe fully walk you through the entire calculation, but let me just say it in words. So what we showed in previous work is that this E bar has the property, all the points in here must have multi-degree which can be obtained from the trivial multi-degree 0 by some twist. Just combinatorially, the multi-degree must be reachable by a twist. And so, if some point here mapped to the green part, then you would have this L of alpha, which is one stable multi-degree on the C hat. But there would be a twist which moves it to multi-degree 0. And by our assumption that the stability condition is small, this would also be stable. But this is a contradiction. So somehow this whole setup of the stability conditions, of non-degenerate stability conditions, says in each such twist equivalence class of multi-degrees, there should only be one stable representative. And so somehow this, just for this kind of numerical statement, you cannot have anything here which maps to the green part. But this means now we're in business, because now we just need to pull back the fundamental cycle of E bar here, and this will already on this log blow-up give us the log dr cycle. Okay. So it seems like we have exchanged our problem for computing this E bar, but the good thing is we did our homework. In fact, we did our homework before we even got it assigned. So we calculated in previous work with Yang-Han Bei, David Holmes, Rahul Pandharipande, and Rosa Schwartz, we had calculated this E bar. And looking back now, we could actually kind of find an even nicer formula than we had seen before, because you can express this. So this Picard stack again has this kind of tropicalization. It has piecewise polynomial functions and so on. And you can express the formula that we had found in some very nice terms, namely just exponential of some class eta hat times phi of some big piecewise polynomial. Take the codimension G part. And then if you pull it back under this map, it just means you need to pull back eta hat, you need to pull back this fp. Eta hat maps to this part of the formula, and the big fp maps to the small fp that we had seen. And this basically concludes the proof. And even though I'm not over time, let me finish the talk. Thank you.
Can you say a word about how the actual formula depends on the theta?
Yes, so well, first of all, the theta determines what exact subdivisions you take, because basically, I mean, somehow, for example, I programmed all of this also, and so you basically enumerate all, given the theta, you enumerate first all stable multi-degrees, and then you enumerate all the ways in which you can twist the degree of this O sum AI pi to this. And this, and depending on what the length of your edges are, somehow some of these alphas with the corresponding slopes can exist or not. So this determines this. And then also kind of the piecewise linear and the piecewise polynomial, they also feature, I guess that once you know what is the representative as a quasi-stable curve and stable degree, I mean, the formula is relatively universal, but it is still true that somehow if you change the stability condition, then it's not so easy to see what exactly the formula. I mean, we had our best man, Aaron, on this task, and he has by now understood a bit about this, but it is kind of a bit non-trivial. But in particular, I mean, in a certain sense, it's a kind of double-edged sword with the stability condition, because you need to fix it to get a formula. Taking a different one gives you actually on the nose a different formula a priori. And you could be sad about this because we don't have a canonical formula, or you could be happy about this, saying that if you take the difference of these two formulas, it gives you actually a relation in the logarithmic Chow ring. And this is kind of a first source of non-trivial relations that you can obtain there.
Any other question?
From the formula perspective, is it clear that the right-hand side push forward to the dr formula?
So somehow I think this is non-trivial statement that Aaron has confirmed to us is true. And I think if you want to know it, you must ask Aaron, because it has not been written down. But yeah, I think you can work it out. But yeah, I mean, doing these push forwards is actually kind of a bit complicated, because if you have a piecewise polynomial on some subdivided thing, there's a general formula by Briand, what, if you take the push forward, what polynomial you get. But it's a kind of weird sum over some rational function weighted stuff. And so you, yeah, it's not a priori obvious that you would get it. Yeah.
More questions? If not, let's thank the speaker again.